Good morning, everyone. A very warm welcome to you all. Thanks ever so much for joining. Very excited today for our webinar on the definitive guide of 3D printing. My name is Justin Cunningham. I'm marketing manager over here at Stratasys. For those that don't know, Stratasys is the global leader in polymer industrialized 3D printers. So covering everything off from applications like very early days prototyping, functional prototyping, high sort of concept modeling, full color, right the way through to tooling and end-use parts as well. So pleased to have with us two experts in the field that have helped around the UK hundreds of customers from the very small to very large get started in their 3D printing journey and well beyond. So delighted to have Matt Jones, who we'll start with, who's application engineer here at Stratasys, and also Rob Thompson, product specialist with our platinum partner SYS, also based in the UK, just by Derby. So we'll start off with Matt, who's going to give us the definitive guide. Matt, I'll be placing you a little bit on time, so we're only going to real whistle-stop tours on different technologies and where they work best in the field. And the types of applications they're suited for. So just about 5 minutes or so for each. So really quick top level view, but then we'll go into the factory with Rob to have a look at the actual machines. You can ask questions along the way if you want to have a look inside the machine at the top. Whatever, please just ask and we can do all of that live. So yeah, looking forward to it. Going to be a good session. So I'll hand over to Matt to kick us off. Over to you, Matt.
Fabulous. Good morning, everyone. As Justin said, I'm one of the application engineers in the UK, and I will try and keep my time down and not waffle on too much. So we're going to give you an overview today of the Polyjet systems, the stereolithography systems, FDM, clearly the origin to the DLP, and also the SAF. And you can see here where they sort of fit in. So Polyjet is prototyping, functional concept models, or sort of full realism. Stereolithography is for prototypes, also for tooling, molds. FDM can be for wide range. Yep. Oh, sorry, other background, sorry. FDM can be used for production parts, tooling, prototypes as well. Then moving into more of the mass production with the P3 and also the SAF. So I'm going to start off with the FDM. And today we're going to look at three core systems. So the F123 and that series, along with the F770, and then our Fortis range of machines as well. So we're looking at our engineering grade systems that can be installed in offices, but can be used for prototyping, concept designs, or engine parts. F770 for large parts, or over 1 meter in one dimension. Big repeatability and uptime and yield rate, and then obviously the production systems that we're pretty much renowned for with some very advanced materials. So looking at the F123, we have three machines that we're going to look at: the F170, the 270, and 370. I believe Rob has a couple of the systems in the office that we can have a look at. They all do slightly different things because of material choices, but also the main difference between the three is the build envelope. So you're at 254 by 254 by 254 for the 170, and then we move up in size for the 270 and 370. But as we move up to the flagship, the 370, we add additional materials like Duran, which is a nylon 6 based material, very good for soft jaws, doesn't scratch or damage parts, but also a carbon fiber filled material called ABS Cf-10. Now, we've recently also announced our carbon ready series. So we have a 190 CR and a 370 CR. So these are systems that are hardened. So the heads are hardened, the drive system's hardened. We've changed some of the controls, airflow, oven regulators and things like that, which are allowing us to do much more advanced materials. So at launch, we've launched the Nylon Cf-10, which is a nylon 6.6 base material. So it's much stronger and stiffer than the ABS Cf-10 on the 370 and the 270 machines on the other range, but it isn't quite as strong and as stiff as the Nylon 12 CF that you get from the Fortis range, but really good strong material, as you can see examples there for press tooling or metal forming as well with this. Again, same build envelopes as the previous system. We're just future-proofing ourselves to allow us to run some more advanced materials that will be coming later in the year. Then moving on to the F770, this is, I call it the wide boy. It's 1 meter by 610 by 610, the build envelope, so we can do some really big parts, but we've only got this in ABS and ASA, so we're limiting the materials for prototypes or for jigs and fixtures on production lines. Very much a production system in with regards to the fact that you can leave it unattended for around 10 days, printing very, very large parts on there. And again, it's leaning on the technology from the F123 and rolling that down, from the F900 and rolling it down onto the F770, so we get that reliability and repeatability that you'd expect. As I've mentioned, big build envelope. It's the largest or longest fully heated build chamber on the market. It's fully heated. We have all the controls you'd expect, obviously links into our software. It's also shop floor ready with the MT Connect software, and it's very, very good. A big beastie machine, and again, we've got one of those at the SYS demo room as well. Moving on to the Fortis, these are our flagships machines. So here we're expanding from, our if you look at the lower end stuff like the F123, and we're bringing it into the much larger system. So there's significant improvements on thermal controls, giving that high maintainability, reliability, and the quality of prints that you'd expect. So the coefficients of variance is in the high 90% percentile, which means you're going to get a part off the machine time and time again. And it's very, very repeatable as well. There's a wide range of materials. So there's Nylon Cf-10, there's Ultem 9085, 1010, there's Antero, so that's our PEC-based materials on both machines. There's also a carbon nanotube filled version for ESD. There's ABS ESD, there's ASA, there's PCABS, there's biocompatible materials. The list is pretty exhaustive. So we have a machine that's reliable and repeatable, and we have a material that will suit most application needs. And in fact, later in the year, we're doing our preferred materials that we announced earlier on. So we'll have even more materials coming to the show, maybe glass-filled materials or low-cost fire retardant materials as well. How do those materials stack up against each other? So one thing to say is that the F900 isn't just a bigger version of the F450. There are significant mechanical, electrical, and software differences between the two machines. But basically, there's a material offering difference. There's an advantage on the F900 of accuracy and repeatability. Clearly, a bigger build envelope as well. So instead of the 400 by 355 by 406, we're at the 900 by 600 by 900 build envelope area. We've got variable tip sizes as well. So we have a T40 tip, which means we can do 1/2 mil slices. So we're printing parts that are better quality at a thicker slice height much quicker than you would get off a Fortis 450. It has, the 900 has built-in UPS, has dew point monitors for monitoring moisture inside the filament tubes, less calibration, has automatic oilers, ball screws, as opposed to belt driven, but both systems very, very reliable and repeatable for manufacturing and production floors. Little slide here I thought I'd throw in about the precision when you compare it between the F370, for example, down to the Fortis 450 and the 900 again. So we're looking at the repeatability, the nominal deviation from the nominal size of the CAD. And here you can see the differences between the 370, the 450, and the 900. The 900 being the main one for high quality, high accuracy, repeatability for production parts. But all of the systems are within sort of 127 microns of where they need to be on sort of large-ish parts. So very repeatable, very reliable. Moving on to Polyjet. Now there's a huge range of machines, and I don't have enough time to go through them all. So there's the J35, the J55, there's the Medijet, the DentaJets, there's the 8 series, and there's also the large 4100 as well. These are all Polyjet systems. So this is where we're taking inkjet heads effectively, and instead of using ink, we're using the photopolymer, and we're doing droplets, and we're curing at the same time with UV light. Now, whether that's a Cartesian system that's going back and forth or a radial system, that's spinning around on the newer machines. And again, we'll give you a demo with Rob on those shortly. But what it allows you to do is concept verification. So whether that's in monotone, so grays, blacks, whites, with textured surfaces, or really quick draft gray mode. So again, it's a cheap Vero gray material that you can pump parts out very, very quick at a low cost to give you that fit, feel, and function to see how you're doing in the concept verification. Design validation, so you can move on to the J55 or the full color systems to do transparent models, different colors, different shore hardnesses with elastomeric materials, all printed in one go. As for that design validation, as you can see some examples on the screen. And then we move on to sort of more functional performance. So we have a range of elastomeric materials. We also have a digital ABS material that's more stronger, stiffer, has a higher HDT, so we can do things like very short injection mold runs, or for tooling applications as well. Really nice. Again, we can overlay graphics with VRML. We can do bump surfaces to apply texture. Transparent like PMMA quality. It's not quite there, but it's very, very good. And again, you can see some examples of overmolding along with the colors and the graphics on site. So multiple materials, depending on the machine, can be used in one go. Moving on to one of our new babies, which is the P3 platform from Origin. So this is a DLP based process, so digital light processing, where you have a projector underneath and you have a tray or a liquid base, and you shine the light through, and it cures and solidifies layer by layer to the build head and moves up. Whether it's one part or it's 10 parts on the same layer, it takes the same amount of time to cure. So it's a very rapid process at curing resin and building them up in the Z direction. Really good material diversity, FST compliant materials, chemical resistant materials, materials for dental, medical applications. Really nice impact modified nylon 6/6 materials for some sort of more trickier applications on production lines or end use parts as well. The build envelope, much smaller than what we have on our other systems. It's 192 mil by 108 by 370, but because it's so rapid, you can produce an awful lot of parts in a very short amount of time. It's also open source, so we're looking at 385 nanometers, so you can put your own materials in if you wanted to as well. We've got over 10 materials already certified by BASF, Henkel, Covestro, and other ones, and they're all one part polymer materials. So there's no need to mix materials and have short pot lives and things like that as well. So it's and also to say the green state of the parts coming out, it's very, very, very high. So that means we have much more reduced post-processing. So you don't need to UV cure parts for very long, sort of 5 to 10 minutes. And then you also don't have the stresses that you're putting into. So you reduce the curl, the warping as well, and you get much more accurate, repeatable parts. Really good for connectors, end-use connectors, whether that's for automotive, aerospace, rail applications, naval applications. It could be for testing drug delivery systems with the biocompatible materials. But because it's so accurate and so repeatable, and you can do like sort of 400-500 small connectors in one go on a build within about sort of 10 hours, you can get sort of thousands or tens of thousands of parts off a year. Some examples from automotive, so connectors here, also has elastomeric based material, so you can do seals, you can do extrusion dies, injection mold tools. Again, it's a very, very diverse range of applications based on the materials that we have to offer as well. Tolerance is as tight as 25 microns. We have a native resolution of 50 microns on the pixel size. Multiple sensors inside the machine to monitor what's going on with separation forces, exothermic reaction from when we project an image and it cures the material, all the way through to the heated build chamber, which is key. So we're able to control the build chamber. So materials like 3955, for example, that need to be maintained at 60 degrees C throughout the build, we can do that, and we can do full build envelope in X, Y, and Z, so solid brick parts if you wanted them, which proves how stable and repeatable the system is. Moving on to the stereolithography range. So we acquired a company called RPS Two amazing platforms, the Neo 800 and the 450. Again, open source, so 355 nanometer wavelengths, but these are industrial, precise, repeatable systems. Gives you amazing accuracy, really good sidewall quality, and as I say, it's open source. There's a couple of versions. The first one being the Neo 800, which is the largest of the systems. The 800 by 800 by 600 millimeters has a 2-watt variable beam size. You can change the beam size from 150 microns to 600 microns. Slice heights from 25 microns to 200, depending on the material that you go for. And we're looking at less than 100 microns accuracy on parts, less than 100 mil repeatably, and greater than 100 mil, we're looking at 150, sort of 200 microns ish. And it's also, as it's the flagship system, it's also 40% quicker than the next machine, which is the Neo 450. This comes in two options. So the 450S, which is the 2-watt dynamic and variable beam as well. So from 80 microns to 750 microns, so you're going to get really good surface quality. And also the 450E, which is a 1-watt laser, 250 micron beam. So the E is basically the base entry level. Again, going to get really good quality, but it's not as good as the S or the 800. So the S is basically the high definition model. Has some amazing materials again, like Watershed, Taurus, Evolve, Perform for high temperature. So for wind tunnel testings, you can do composite layup tools, amazing surface quality. So if, for example, you were used to getting layup tools from FDM, but you spend 2 to 3 days post-processing the part to get the RA value right, obviously you don't have that post-processing time with stereolithography. You know, with the materials there, you can take them off, remove the supports, do a little bit of fettling on that, but the overall surface quality is very, very, very good. Also for casting, wind tunnel testing, injection mold tools as well, some really good applications there. Hopefully I'm doing all right for time, Justin. Last section. So this is again a new technology. So our SAF technology, selection, absorption, fusion. Looking at high throughput. Again, these systems have very, very tight temperature controls, which gives us the reliability and repeatability of parts coming off the machine. And it's very economical as well when you look at the single fluid that we use for absorption. This machine has a build envelope of 355 by 250 by 345, depending on the density and how you pack it. So we're leveraging the SAF technology into this production platform, and it's designed to deliver functional production grade parts with unrivaled consistency. So it's going to allow you to grow your business, the demand, the supply as well. Really good for consumer goods, electronics, orthopedic, medical applications, clearly for service bureaus, transportations. You can do small or large bulky parts, molds, brackets, machine components as well. How this machine works, basically we have 2 heads, and we're trying to get, well, we do get homogeneous fusion with our process, so recoating, heating, printing and fusing. We have you know, 70% recyclability of the powder as well across the bed once you've print your parts. Really tight uniformal tolerances with the thermals and the dynamics from the machine. It effectively works like this. So we have 2 sleds with a preheating lamp and a roller, and we have a big wave management system where we're pushing the powder across and it goes down and gets recycled back up. That's the sled you can see on step 2. It's pushing across. Obviously we're doing the single fusion, and then we're using IR lamps to irradiate that and heat it with really tight controls. So it's not going back to front, left to right like some technologies. It's left to right, right to left. So it's much quicker. We also don't have the cold spots as well, so we have much more thermal control over the entire area. With this technology, there's no hidden costs. So the print heads, for example, are all included in the service contract. There's no cleaning rolls, no lamp filter. You don't need the processing station fan filters or many other filters that are required typically with powder-based technologies aren't there. Lower costs because of the fluid. It's only the one fluid. So significant cost savings and build time savings compared to other powder-based systems out there. And that's it. Hopefully that was quick enough, gentlemen.
What a whistle stop! When we said to Matt earlier to try and fit in all the technologies as quick as possible, I think you nearly had a heart attack, Matt. So
I did.
thanks ever so much for that. Oh, my camera's not working. Hopefully it will kick in a second. There we are. Excellent. I've had a few IT gremlins today, so glad that's over and done with. Right, so now the exciting bit. So Rob, I think if we can get you to maybe give us a tour and we'll have a look at some machines. For those on the line, please just ask your questions. If you have any questions about specific technologies, we can answer those and we can have a quick look around the machines. Just as a very quick recap from what Matt was saying, 5 potential technologies there. Polyjet, mostly used for prototyping. Neo, also prototyping, but can be used for things like investment casting and tooling. FDM, real thermoplastics, often used on for tooling, factory floor type applications. And then we get into the production systems, which is Origin, our DLP solution, as well as SAF powder bed solution. So real production parts, sort of real trying to fight against the traditional manufacturers there and offer an alternative. So so Rob, yeah, I guess if you can start us on the tour, that would be wonderful.
Yeah, morning everybody. Thank you for joining us, and thanks for that, Matt. It's like you say, a lot to cover in such a short period of time, and you know, again, just a quick walk around of here won't tell everybody everything in full detail, but hopefully we can give you a bit of an overview of each of the machines. So here in the demo center, we've got, as you can see, a range of system. Hopefully, people are seeing that on the screen now. I think, you know, whilst we're at this point, we'll start off with the Origin machine. So the Origin machine here has been here now around about 2 or 3 weeks. This is a technology, as Matt says, which is a DLP variation. So this system itself has got a head inside it, which is going to just release the door there for us. This is the head here, which is going to sit down in the bed, where we're going to have some resin inside there. And we're also going to be measuring things like pull forces, temperatures, a lot of control with inside this chamber here, which allows us to use some quite interesting materials. And as Matt was alluding to, a lot of these materials can be potentially used for end use. We've got real high surface quality and accuracy on these parts. I've got a little range of parts here, which hopefully, if I can get the camera right, should just show you some of the detail and the feature definition that we've got with this machine here. And essentially, this machine is pretty much good to go. Straight off the bat, you can see the system itself is quite a nice size. There's some post-processing that you have to go through to actually process the parts. So once the parts are cured, as Matt was alluding to, cured to a very, very high green state. So in some DLP technologies, you know, you've got to be very careful to take the parts off and then post-cure them without losing dimensional accuracy and stability of the part. In this particular instance, we've got a very high curing state directly from the machine. The parts can then be taken away, cleaned in an IPA bath, and then post-cured in UV for a very short period of time, which again gives us more control of the process, and it sort of opens this all more to be used for end-use parts. I've left the screen on here, which would be measuring the actual temperature of the resin in the tray itself. But I don't know if you've got anything else to add on this one, Matt, or whilst I'm here.
Yeah, so at the moment we're building slice heights from 100 microns to 50 microns. So the part that Rob showed was built at 50 microns. And even when you look at parts printed at 100 microns, so basically the worst we can do, the surface quality is exceptional. It's very, very good. This machine uses pneumatics as well. So we have a pneumatic separation process. If you wanted to do the OML, so the open material license, you are able to put different types of inert gases inside at the back of the machine. So it's already kitted up for that. So if you wanted to make your own materials or more advanced materials, or run something that we don't currently offer, that option is there. The image is showing the infrared camera. So we're monitoring the oven temperature, we're monitoring the exothermic reaction per layer when it cures. We're also monitoring the temperature of the material, because obviously viscosity changes depending on the cross-sectional area that you're exposing. So there's a lot of sensors in there, there's a lot of software in there, and it's significantly an improvement over others out there on the repeatability and reliability. And it's honestly, it's mostly down to software and sensors and what we're looking at as well. It's very intuitive. So Rob mentioned about the build head. I've worked on many DLP machines over the years. There's a lovely little video that you tap on the screen. There's a torque screw there. You release it, it comes down, it wobbles. You push it onto the build platform, lock it off with a torque screw, and it's done. And it's a really simple 5-minute calibration to do the offset. So yeah, all around a really good machine, and the materials are fantastic.
Yeah, so as I say, we've had this machine for around about 2 or 3 weeks now, and we've already cracked on and printed, benchmark parts for customers. We've found it, it's to be fair, our first DLP experience here at SYS, but we've picked it up really quickly, I must say, and we've been so impressed with the quality of the parts. When you're looking at low volume production parts where you need high accuracy, high surface quality, injection mold surface quality, then this really is a technology to look at. And I mean, another key feature which I think you touched on in the presentation was the single material, rather than having to mix 2 materials here. So the pot life of the materials is around about a month once you've opened the actual the bottle of the material, so you're not wasting material at all with this process. You just have to put into the machine, into this tray area here, the amount of material that you actually require. Once you've printed the parts, if you want to change materials over, it's pretty straightforward then to take out that tray, pour that material back into the bottle, and then start up with another material with different properties.
Yeah, you can fit around about 2 kilos of resin into that tray. It looks a little bit deceptive, but you can put 2 kilos in there, so that's going to produce a lot of parts in one go on the machine. It's also the tray's locked down by magnets as well. So,
so you've got a tray release there on the screen. I'd need 2 hands to lift it out though, unfortunately, so I'm not not going to attempt that whilst holding this iPad. So yeah, fantastic bit of kit.
A couple of questions that have come in. We've talked surface quality and surface accuracy, but what about overall dimensional accuracy if we take the whole part? Do we have any figures on that, plus minus?
Yeah, so the coefficients of variance, the repeatability, so most parts that you're going to get off that machine will be around about 50 microns or less on there. So there is actually something very nice from Origin and Stratasys is we've published repeatability data with regards to accuracy for different materials. So you can see the mean value, the standard deviations away from them across multiple materials, across multiple platforms. You can download that from our website. We've also produced a mechanical repeatability study from it as well. So obviously printing different parts on different, same parts on different materials on different machines, and then doing all the pull tests, mechanical tests as well, just to see how repeatable we are from machine to machine, from build to build as well. So yeah, we have that data available, but it's a very accurate and precise machine. And obviously, if you wanted it even better, then you can basically adjust the shrinkage factors and get it even tighter.
And another question that came in was about build time. So if we can talk maybe build times in comparison to other machines.
Yeah,
it's one of those. It depends, doesn't it?
Well, so it's obviously the Z height of the part denotes how long it's going to be, but we vary from 100 mil per hour down to around about sort of 30 mil per hour, depending on slice height and material exposure times as well. So most of the parts that if you've had chance to look at them or see any and touch them, they will be done at 100 or 50 microns. So they are very quick at coming off. So for example, an exposure per layer could take something like 2.7 seconds. If you take into account Z stage movement and coming back down and waiting, it's like 3 seconds a layer. So, some of them are as high as 4 seconds a layer. Some of them are lower down to the low 2.2 seconds a layer. One thing to say is, as Rob's got the part in the hand, because of the high green strength and accuracy we have much greater span distances. So depending on the material, so from 2 90-degree angles, we can get away with maybe 4 mil or up to 10 mil worth of a span distance without the need for any supports, without any delamination as well. Some materials require much less support, so elastomeric materials need more because of the nature of the beast. But when you compare it to other DLP technologies, you need less support again, which means less material usage and also less post-processing.
Yeah, it's worth mentioning. Sorry, it's just worth mentioning the machine is only just a 3-pin plug power, and you know, networking, you can send the jobs via Wi-Fi, or you can have it with an Ethernet connection on there as well. So very easy to implement bit of kit as well. It's not something that, you know, requires you know, a dedicated room or facility necessarily.
Lovely stuff. So let's get on to the next technology and machine if we can, because I'm just conscious of time. So
we'll drop onto the
H350.
yeah. So the SAF technology, selective absorption fusion, as Matt was saying, a new technology which has been born out of a combination of Stratasys and Zara, a UK printhead company. And I do believe the print heads come from a derivative of heads that were used in the ceramic printing industry. So a very dusty and hot environment. Obviously, the more control we've got over the print head technology, and the more control we've got over the chamber, then the more consistent the print can be. And that's where we're really aiming at with this technology for production parts, for serial production in the thousands of parts. So if I can lift the lid, it is quite heavy. See if there we go. Get the lid up on the machine with one arm.
Working.
That's it. You can see the carousels that the carriages, sorry, that Matt was talking about. We've got one here at this end and one at the other end here, and that would then deposit the binder. Would start off by depositing the powder into the build tray. This platform would be starting up at the top of this build platform here. Would deposit that powder over to the to give us a layer of powder on the bed. Any excess powder would go down this chute here and would be recycled back into the machine. So as Matt was saying, we've got a very high recyclable rate of powder, which, as people using powder technology will know, is key to getting your yield, if you like, and your throughput and your part cost down when you're doing production parts. We'd then be putting the binder into the 2D pattern, if you like, into that layer, and then the infrared light would actually be reacting with that and fusing those particles together, and the process then repeats itself again and again. Now, what we gain by doing that in one direction like this is a very uniform way of working, which means that all the powder that's been laid down and all the binder that's laid and the parts that are being cured have been down at the same period of time. So we've not got random areas within the build that have been laid down longer and shorter, so that when we actually get a full cake of parts, we've got a much better accuracy across the build area. So if you're printing many thousands of the same component, they're all going to be accurate and going to be printed to the same tolerances.
Yeah,
Do you want anything to add anything there, Matt?
Yeah, a full cake will probably take you, I think it's 14 to 16 hours or something to build. So nesting density is you know, anywhere from 12%, 15%. So you're much higher nesting density and packing a lot more parts into the cake. I say print time's pretty damn quick. You take it out and you can put it on a shelf to cool down and put another one in and press play. So it really is a production system. Obviously, you've got the full suite of post-processing afterwards, so with dimension or other technologies out there, so you can dye the parts. Obviously, there's PA11 on there, PA12 coming, and PP coming as well on there. That's how you top up the powder through there. There'll be other things coming out later for the machine as well. But if you look underneath the lid as well for us, Rob, you can see underneath the actual heater. So you've got all the ceramic heaters, the sensors, the camera, the IR in there as well. So it's an absolute beast of a machine, and we're talking very, very high production, high surface quality as well. You don't suffer from the downward facing surfaces don't suffer from orange peel effect, the way we nest together. So again, really good surface quality, mechanical repeatability, as Rob was saying. It's not just about temperature, but because we can control that temperature, part or yield to yield, build to build, the mechanical repeatability is phenomenal. And these machines, although it's a new technology for a lot of people in the market, they've been out there for a few years now on beta sites at service bureaus, and they are a proven, reliable system. Even though they're new to the market, there's people that have had them for years and have pumped hundreds of thousands of parts out of these machines. Really good kit.
We've got some significant advantages, as Matt was saying there, you know, in terms of packing densities, recyclable rate on the materials, but also some of the consumables that are used in these processes. We've got very few consumable items in this process. So there's no detailing agent, for instance, in this particular technology. We're only using one binding fluid, which is giving us a very high infrared cure on the parts. So we only have to use one fluid on this machine. So when you look at this sort of technology, people would usually be considering this type of technology for end-use parts and with a high enough throughput. And when you consider an application like that, then you've really got to look into how much those parts are going to cost you long term. And so that's where, you know, if people need this type of technology, want to consider this type of technology, we'd have to come in and work with you really on the return on investment on printing the parts rather than producing your traditional methods. And that's where it's key then to think about the print head costs, the binder costs, and all of the other consumables that are part of this. So our print heads are all part of the long life warranty on this machine. You don't have to replace those print heads regularly. So that's really where we've aimed this at the real production end of the market.
Yep. So if we took brackets and clips, for example, clearly we could do that on FDM, and it works really, really nice. But when you do that on the H350, because the volume is so much bigger, production speed, you know, the cost per part drastically drops down. So, you know, if you print one part or 20 parts in FDM, the build time clearly increases. So whatever you can ram into that cake on the H350 and get off within that specific time, you know, you can really ramp up the production to tens of thousands of parts, depending on what you're doing. The surface quality is phenomenal as well.
Yeah, just showing a few parts in the cabinet there that you can see. So the grey parts here that you can see have come raw off the machine. They've been depowdered and they're good to go, fully cured and ready to go. This darker coloured black part that you can see here at the front, that's been through the dyeing process that Matt mentioned there. So, you know, you can dye the parts in quite a crude way if you want, you know, just literally dyeing them as you would do, you know, with a liquid dye. But also out there nowadays, there's so many post-processing options with really professional companies like Dimension and so on that have equipment that will help streamline the post-processing for any powder technology out there. So yeah, I mean, our system comes as a turnkey solution, comes with depowdering station, comes with the build box, which allows you to take the cake out of the machine, so that once you've taken one build out of the machine and you're working on that build, you can start the machine going, so you can get going on the next cake of parts.
So a couple of questions that have come in for people on the SAP is, once the build's printed, how long is the cooling process? How long do we have to wait before we can decake and get the part out?
So typically you're going to leave it overnight. So 12 hours, 24 hours is the typical time that you would do, obviously, to reduce thermal shock to the parts inside. So it's a typical process for sort of unpacking the build. But again, it'll be specific to the materials, and we'll have the guides available on the website for you to have a look at.
And just to understand, you can take the cake out, let it cool down, and carry on building, you know, with another build. You don't have to leave it in the machine for 12 hours.
No, you don't. And obviously the powder that's being decaked is as we say, is totally reusable as well. So, you know, that can go back into the machine, in the mixing station, you get the ratios there, and off you go.
And a couple of questions just to clarify. We always assume people know the language, but just what we mean by cake and nesting, because they're kind of not typical words when we talk about the other 3D printing technologies. We talk, yeah, probably different, like build volume rather than a cake and nesting. Yeah. So go on, Matt. Sorry.
So the cake is basically that whole volume area that Rob's showing on the camera there. That gets lifted out, and it looks like a solid white powder cake, basically. So it's like, you know, when my mum used to make cake and there was powder everywhere. Not the case here, but it's that big solid lump that you get afterwards. And then the nesting, my analogies really do suck. I'm sorry. The nesting density is, okay. The nesting density is how many parts we can cram into that powder cake. Obviously, you can't have parts touching to each other. You can't have parts too close because of the detailing agent, the SAF fluid on the side. But because we only have the single detailing agent, we can nest things much closer together. And because we have that tight thermal controls, it also aids us to have a higher nesting density, even though it's maybe a slightly smaller build envelope than others. Throughput is better.
Lovely. So let's move on to the next technology if we can there, Rob, but I'll ask a couple of questions along the way, and please do keep your questions coming for the guys. Question here, I guess it's kind of looking at all the technologies. What's the minimum wall thickness we can achieve? I guess it's probably Origin, but maybe Neo.
It's a great question. Minimum wall features can be as low as 250 microns, but the thing is, it's consistency and repeatability, and also the materials. If I print on a Polyjet machine a wall that's 0.5 mil thick or 300 microns thick, it's going to be very easy to snap and break it. If it's just as a visual concept model, then fine, so be it. If you're looking at very thin walls that you want to work, then it's not going to be. The Stereolithography and P3 will allow you to consistently build 0.5 mil wall thicknesses with the strength and stiffness that you require. You can do, you know, 1 mil on FDM if you change, depending on the bead extrusion widths and things like that. Again, but it's usability and functionality of the material. So Polyjet's really good for microfluidic channels. We have water soluble support, which I didn't mention earlier. But I'll let Rob carry on with the demo, otherwise we will run out.
It's they said, yeah, I'll start with the Polyjet now. We'll start with the J35. So this is a pretty recently launched machine, a desktop system. And those that know Polyjet's been around for, you know, probably 20 years plus now. It's a very established technology, and they'll perhaps know the trade name of Connex. And we were very well known for our Connex 3D printing Polyjet machines, which allowed us to plug in multiple resins into the machine and you know, create overmolded parts, blend those materials together to create various digital materials with different Shaw values, Shaw values, and potentially colours. Now, that technology has moved on a long way now. It allows us to actually plug in more materials, and it allows us to use software now, much more advanced software, things like Keyshot, to bring out the colour. So the J35 is what we would consider one of the entry-level machines here, a desktop style machine, as you can see, with a very small footprint but quite large build platform. And this is one of our first rotational systems here, or radial systems. So you can see the build platform is this area here with inside the machine. And if I can just sort of angle up, it's just this blue light may just stop you seeing it, but the print heads themselves are at the back of the machine here, and they traverse into the center of that circular build area. The build area would start up at the top and work its way down. So in this particular machine, we can plug into the system 3 different modeling materials and then our support material as well. So on the tray in one hit, we could print a clear part. If I take that away from the blue light, you can see that a bit better. So we've got a clear part there. I've got a white part here, but that's actually an elastomer material, as you can see there, for like an aperture seal. And I've also got a part on here which has got multiple materials in there as well. So that part's been printed with a nice soft touch rubber sort of leather feel there onto that, with also some grayscales just to sort of define those different areas that would be on that gear stick. So this machine here is really powerful. We don't use colour on this machine. It's a monochrome machine. It allows us to use clear, various rubbers, and various different materials like digital ABS will take us to the higher level of prototyping in terms of the Polyjet world. So HDT around about 100 degrees, tough parts that can be used in functional testing. So this machine here is an absolutely brilliant choice for people who are doing prototyping, need a quick throughput. We've got that quick radial build that's spinning there, and they need multiple parts for different areas of the business. You might be working on lots of different projects at the time. It can all be printed on one tray at one hit. It's only a 3-pin plug as well, this machine. So you can see that system there. The slightly bigger version of that, which is the J55, you can see here it's got its own base to it. This then, as the name sort of alludes to, allows us to plug in 5 base materials as opposed to 3. So you can see here we've got our base materials, and you can see straight away, I'm not sure how clear it is on the screen there, but we've got cyan, magenta and yellow, and we've also got white and we've got clear plugged in. And then our final material again is our support material. And as Matt said, the support material with Polyjet now can be washed away with just water. You can leave the part soaking in just fresh water. It will dissolve support material. Although we still have a lot of people utilising a water jet to wash the parts off. The parts from a Polyjet machine come off fully cured. straight off the machine, and the support material is like a waxy jelly sort of feel to it, and it can be just broken away very easily with a water jet. So the parts can be in your hand and ready to go straight away. So for design consultancies, for office-based design teams, this is a really popular choice of technology. So the J55 then, as I say, allows us to plug the colours in, and with some really clever software that's been developed, we can start to do parts like this here. So you can see this part here. Oh yeah, though yes, we have washed the support material off this. I don't want to sort of mislead you there. We've washed the support material off this, which would have took, you know, a couple of minutes to do that on a simple part like this. That is straight off the machine surface. You can see that lovely glossy surface. That's a natural finish that we get from the Polyjet process. So on the top surface, we can gain this nice glossy finish, which again, to get a full colour part like that is just astounding. You can see some of these parts here that we've got textures, colours, text, really taking things to the next level. Nice part here which has been polished up afterwards as well. So both of these machines here, the J55 and the J35, a 3-pin plug. We've also got a new aero system which is cleaning the air out of those machines as well, so there's no funny smells or anything like that within an office space. And it's a really competitive technology if you want to think about bringing prototyping in-house. It covers such a wide range of what you'd be doing from a prototyping point of view, perhaps either with a bureau or on various different machines that you've got there. You could consolidate that down all onto one industrial professional printer. So moving on from there, we then have a machine like the J850 Prime. So this machine here is more of our traditional Cartesian build bed. So you can see on this system, we've got the tray up there. So we've got 500 by 400 by 200 in the Z on this machine. We've got our print block, which has got our UV lights either side and our printing heads, and we'll spray that material across this bed in this natural sort of angle that people would sort of consider as most printing technologies would be in that kind of orientation. We've then got a much larger array of materials. We could actually double these up in our material cabinet here, and these are 4 kilo canisters as opposed to 1.1 kilo canisters on the other machines there. So where would you go for this machine? A more industrial system, you know, something that's going to give you a similar output to the other 2 printers, but on a larger scale, you know, with higher throughput. So, you know, design teams in the 10s or in the 100s perhaps would take advantage of something like this. Service providers, service bureaus, where they could offer a printing service. You know, with all of these different materials that you could have plugged in here, you could have colour, clear, rubber, mixtures of all of those all on the tray at the same time. So Polyjet remains, I believe, probably the most powerful tool for prototyping, for concept modelling in our range. You know, it's a really powerful technology, very easy to get into as well. All of our machines in Polyjet, barring maybe the 4100, is a 3-pin plug, so you don't have to worry about any 3-phase power. They're very office-friendly systems. Don't know if there's anything you want to add on Polyjet, Matt, whilst we're here?
Oh, you've smashed it, Rob. Perfect.
We know a bit about Polyjet.
Bad.
Sorry, I lost you there, Justin. Have I got you back? So, not got you, Justin. I'll carry on with the F series range. Can you still hear me, Matt?
Yeah, I can still hear you, Rob.
Yeah. Have you? Yeah. Your microphone's gone a bit funny, Justin. So I'll carry on with the FDM. So we've got the F series machines here. So we've got a couple of F370s, which are in the F series range. In here, we've got our build platform. So we're utilising a tray which we print the materials directly onto, as you can see here. So that means that we don't get any peeling or warping of the parts. A lot of people with entry-level FDM machines will potentially see the peeling off the bed as one of the major issues that they get when they're printing with FDM. We've got a material drawer here. So again, the materials are kept in here. There's very little moisture that can get inside here, allowing us to print with very consistent results. And then in the top of the machine, we've got our printing heads. So we're using a printing head which has been specifically designed for the F-Series. You can see the filament tubes coming in here with the model and support material. Most of our materials on the F-Series are utilising a soluble support material. There's a couple of materials where we do use a breakaway only, just on the higher temperature. So these will then deposit the material down onto the tray, so you can just about see those two tips here. So that tray would start up at the top and work its way down. Using the software, we can change the layer thickness that we'd like to utilise on this machine. So most of the materials allow us to print between 127 microns through to 330 microns, so a play off between speed and surface quality. And as Matt was sort of saying, with the F370, we can go everything from a PLA material, TPU material, to an ABS Cf-10, which is an ABS with 10% carbon fibre inside it. And we've just launched now, last week, the F370 CR and the F190 CR, which you'll notice on some of the marketing material we send out, effectively very similar looking machine to this, but with black panels to sort of differentiate the two. And that machine, or those machines, can utilise this new nylon material with a 10% chopped carbon fibre in there, which is I've seen being used for some great applications already in some of the testing that we've done with that material. So yeah, I don't know if you want to mention how that sort of stacks up against some of the other nylon carbon fibre materials, Matt.
Yeah, so it's much stronger and stiffer than our ABS Cf-10, but it's not quite as strong and stiff as our Nylon 12 CF from the Fortis range, but it's substantially stronger than maybe other people's nylon filled materials that are out there without continuous fibre on the inside. So if you pulled the data sheets off and compared them, you'd see a stark difference. Just to say, the F370 is an out-and-out workhorse. You can throw stuff at it all day long. You can not be very pleasant to it, and it will just pump out parts. It's a really good bit of kit.
Yeah, fantastic machine. We've got so many of these machines out in the field in the UK and Ireland and worldwide. It's been an amazingly successful print of the F-Series. Offers great throughput for prototyping. FDM remains one of the most popular printing technologies out there. Obviously the entry-level FDM machines out there give people a great opportunity sometimes to dip their toe into 3D printing, and I think ultimately that convinces people that they do need a printer in house and the benefits of that. And sometimes it's tricky to justify that first machine, but once you've done that and you realise the benefits of having a printer in-house, this is a fantastic next step. So we do offer things like a trade-in program where you can trade your older machine in for something like an F-Series. And if that's the sort of application and things you're thinking of, then do get in touch with us to have a chat about that. So going up to the next scale, Matt was sort of suggesting that this is a bit like a hybrid between F-Series and Fortis, and I think he's right. So you've got the build volume here of equivalent close to a 900 machine, a metre in one axis, which is absolute huge build volume, as you can see here. Hopefully the screen's doing it justice. See my hand. Yeah. You can fit in there, Matt. It's a bit warm at the minute. So again, one thing to mention is the temperature control we've got in here. So we're controlling the temperature. Stratasys are well known for the oven temperature control, and so even on a large build chamber like this, we're controlling that temperature inside there, which means as the part's growing and being printed, we're not losing any dimensional accuracy on the part in terms of it cooling and warping in different areas of the build chamber, and that's really important in the FDM process. So yeah, we've got some of the features from Fortis on here, which is going to increase the throughput, reliability, repeatability, but we're still using a very similar delivery system to the F-Series, the same printing head technology. And you can see, hopefully under here, if we get a bit of light on the screen, there's the material canisters as well, or material boxes in this case. So they're much larger material boxes on there, which is, of course, for larger prints, is going to give you unmanned printing for up to around about 10 days if you're printing real large parts. So something such as this part here, which in the past we'd have had to have printed in one piece, you can see that's in two pieces, and we've sectioned that part there in the past and bonded it together. We can print that part all in one piece now. So perfect for obviously large parts that are going to be for prototypes, where you might be committing to a mold tool that's tens of thousands, if not hundreds of thousands of pounds for one particular application, or for producing some of those shop floor aids, jigs and fixtures that are complex and expensive but still need to be large.
Prints in ASA, Rob, ASA and ABS soluble supports, so you can do really complex designs and just wash the supports off afterwards. You know, if you wanted to build that on, for example, a Neo 800 part, you wouldn't be able to fit. You'd have to section it and chop it, multiple builds. You know, if you don't want these large functional parts, then the F770 is perfect for it.
Just can't get around the back of this machine, but yeah, so your filament goes directly into the back of the machine. It's a 3-phase power on this particular printer as well, just to mention on this machine. We're struggling with you, Justin. I can't hear you.
Yeah.
So I'll move on to the Fortus technology. So we are well known for industrial FDM. You know, Stratasys has been around for 35 years plus, I think now. The founder of FDM technology, the inventor of FDM technology. And so we've had a great advantage in terms of building up a history of developing FDM machines that are reliable and repeatable, and materials that are used within a day-to-day environment. And so the Fortus 450 machine particularly is, I think there's over 2,500 machines out there in field in this version. And we've got a lot of people that are using these anywhere between prototyping to end-use components. And I think at the moment we've got 50 and 60 materials. There was even more materials launched last week with some of the material partners. So there's a glass-filled nylon material, which is a flame retardant. We've also got a closer to peak semi-crystalline material as well from Victrex. So this technology now is being unlocked for those material partners to develop and bring to market some of these materials that are going to take this to even the next level. So on a system like this, we've got our material canisters here. So we can have 2 model and 2 support material in there. We've also got our build chamber. Again, you can see just how industrial this is. Inside the actual system itself, we've got the heated chamber. And you'll see, you know, there's various systems on the market that will be similar to this technology, but as I say, it's the history of working with a heated chamber and working with these complex exotic materials which puts this system on another level. And so straight off the bat, you're working with materials that are out there. For example, materials like Ultem 9085. The Stratasys machines are certified to be working with parts for Airbus, Boeing, people like that. On a larger scale then, you still got me, Matt?
Yeah, I've still got you.
I think Justin's having a nightmare. I'll continue on. I just want to make sure you can hear me good.
There are some questions in the chat. Unfortunately, I can't see them. I'm trying to get Justin to allow me to see them now, so we'll try and go through the questions in a minute once we finish. Sorry, guys.
Cool. No worries, mate. IT always lets us down. So you can see here the Fortus 900, obviously significantly larger bit of kit. Now, when you are starting to print with materials that have got HDT of over 300 degrees C, you can only imagine the temperature that you've got to elevate the build chamber and also the actual printing tips themselves. So you can see the printing tips inside here. We need a lot of control inside there, so you need a lot of power to be able to do that, because some of the builds in here could go on for a number of hours, you know, if not days. So you can see that the physical size of the door on this machine here is quite significant. So a machine like the 900 would be absolutely ideal for, again, those end-use part applications, for high throughput of parts that require printing in a particular material, one of the exotic materials that we're utilising. So what I would say with Fortus is anything where you believe it could be end use, this would definitely be a technology to consider, particularly jigs and fixtures with FDM for one-off parts. It's a great technology. So, I mean, just in the cabinet here, you'll see we've got some end effectors like this end of arm tool here. We've got CMM fixtures, as you can see here, soluble cores for autosport. And a great application, one that we've just really picked up on in the last year or so, is this soft jaws. So you can see that's a machining vise there that will sit on your milling machine with your 5-axis, and then we've got a set of soft jaws in here. So effectively allowing you to print the soft jaw for a second operation without having to take up machining time, valuable machining time, which you could be charging out to customers. So that pretty much concludes the walk around. I don't know if you've managed to get any questions, Matt, or
Any questions? No. I can't hear you. Rob, are you still there?
I've still got you, mate. Yeah.
Are you able to see the questions in the chat field?
I can't, unfortunately. I can't see the questions, so maybe we'll have to collate those.
Modern technology. I've got a picture.
Right.
Yes, so the SAF technology is homogeneous for sure. We've got studies on that as well. Is it suitable for food processing type environment? No voids, bacteria growth. Relating to the SAF technology, then obviously the surface will have peaks and troughs, so you could get bacteria growth in there. However, you could seal the part with a food safe coating to avoid that. Are there any images of the powder reprocessing station? Yeah, so if you go to our website, you can go on to the H350 technology, or you can reach out to the guys at SYS and they'll run you through all the equipment. So not just the machine, all the post-processing equipment that comes along with it. How does the system deal with higher density pixels towards the center of the circular build platform compared to the outside? So for the J55 and 35 series, we have inner and outer swathe. So 1, 2, and 3 different paths. So we compensate for that basically on the fly, so you don't have any issues with the volumetric pixels effectively that we're printing. So it's all compensated for. So whether you got it on the inner swathe or the outer, you'll get exactly the same surface quality and accuracy. If you print on the inner circle, it'll print quicker because the head doesn't have to move as far. In essence, what's the highest temperature resistant material we have? So currently that would be the Ultem 1010 on FDM, which is 213 degrees C, or it would be the 3955 material on the P3, which is 280 degrees C. But there will be a newer FDM material coming on the Fortis 450 as part of the preferred materials that will be around the sort of 260 mark degrees C later on. Yes, we use our 370 more than any of the others. Thank you, Dominic. SAF technology, how do you get on? Yeah, we've answered that one. I think that's everything. JC, Justin, nod if you can hear me.
Can you hear me at all now?
We've got you.
I do apologise, everyone. Absolute nightmare. I was on to IT this morning to install a new printer, and whilst the printer works, I think it's knocked out a few other things. So I do apologise, bad timing on that behalf, and I wasn't able to ask many of the questions that we hoped to get through. But I think we've got through most of them. Have you covered off what's the best way for us to start the process with SYS? Right at the end, we're exploring. So let me ask this one: we're exploring 3D. What's the best way to engage and just get our sort of ball rolling when it comes to 3D?
Yeah, just get in touch with us here at SYS. You know, contact us, give us a call, drop us an email. We can set up a meeting. We can come and visit you. Is generally the process. So we'll take a look. You know, if you're an industrial company, then we'll usually have a look at walking the production line with you. If it's a jigs and fixtures application, start to identify some of those parts that could be printed that are, you know, you're outsourcing for perhaps to be machined or, you know, particularly expensive at the moment. If it's an R&D application, then, you know, we can come in, take a look at some of the prototypes that you're producing, and we can make some recommendations on what the best technology would be. So yeah, I'd just suggest that people would get directly in touch with us. We always offer a free sample part for people once we've taken a look at the application, if it's suitable, of course. So yeah, please do get in touch with us.
Thank you very much. And now you can hear me. I'm just in time to close it off. So I'll close it off there because I think we've got through all the questions. But I'll just do a quick plug for TCT that's coming up in just a couple of weeks, June 8th and 9th. The SYS team will be there with many of these machines, parts from all of the technologies. You'll be able to get hands-on, see the surface quality, see the surface surface quality and build accuracy is the word I was looking for. Flustered at the moment. And kind of get hands on and talk about any specific applications and needs you might have, how it might how particular parts might differ between technologies and also compared to traditional processes as well. These guys are real experts in telling the differences between all of those variables. So it just leaves me to come in and say thank you so much, gents. Sorry I've been a letdown on the technical front, but you've been absolute superstars. Thanks, Matt Jones, as always. So much knowledge.
Justin, sorry. There's one question. So TCT is happening at the NEC in Birmingham.
Yes.
And can I suggest it's only a couple of days a show and it gets very, very busy. So if you do want to have a chat, try and book a meeting or try and get a slot with the chaps. I'll be there along with a couple of the other AEs and some of the other team members from Stratasys in the UK. So yeah, that was it. Sorry.
Yeah.
No, absolutely. And also we're follow up with you with an email, so you'll have contact details to get in touch to book those meetings, and also the presentation from Matt to watch back as well and share with colleagues. So all good. And leaves me also to say thanks ever so much, Rob. Fantastic tour around, great facility, really enjoyed it. So thanks again.
Yeah. Great stuff, and an open invite for anybody who'd like to come along. We offer a demo centre here to anybody who'd like to come and have a look. Any size of business, any size of application, you're more than welcome to come, even if it's just enlightening yourself on the technology. So again, just get in touch with us to arrange that.
Lovely stuff. Well, thanks ever so much, gents. Enjoyed it, although it was one of my more stressful webinars towards the end, but enjoyable as always and learnt a lot. So yeah, have a good rest of the day and good rest of the day to everyone on the line. Cheers.
Great stuff. Cheers. Thank you. Thanks for joining us. Bye.
See you guys.